he's going to tell us about eigenvalue statistics for random CMV, and CMV is
Cantero Moral Velasquez.
okay. I was going to guess something else, but matrices.
Well, thank you very much. It's a great honor and pleasure to present this work here. And so I will explain, I'll spend quite a bit of time explaining what CMV matrices are, how to randomize them, what I mean by eigenvalue statistics. I would like to start by saying that most of what I will present here is joint work with Rowan Killip from UCLA. And I would also like to thank Professor Spencer for encouraging us to pursue this line of research some 3 years ago. That's when we were thinking about this question. And also Jean Hobaik from University of Michigan, Michigan also encouraged us. So, and I can now talk about a full picture of this eigenvalue statistics for random CMV matrices. Okay, so let me start by saying that we will consider CMV matrices, which are unitary matrices. And we will see that they are the unitary analog of Jacobi matrices. So, and we will randomize the coefficients. And we study the statistical distribution of the eigenvalues of these matrices. And let me start by showing a plot. So we will see, so these are unitary matrices. And the eigenvalues are random unitary matrices. So the eigenvalues are random points on the unit circle. And we will see that there will be 3 regimes. A case when we have Poisson distribution of eigenvalues. So imagine here I have 70 points randomly distributed, non-correlated on the unit circle. Poisson distribution means no correlation. So typically we will see a plot like this with gaps, with clumps. I have a pointer here. So you see gaps and clumps. That's an indication of the Poisson distribution. So for certain random CMV matrices, we will have these eigenvalue statistics, the Poisson statistics. Then we will have the critical case, and I will talk more about this, and the the case of fast decay when we have clock statistics. So let me equidistant, yes, exactly like the ticks on the clock. Imagine that you have 70 points on the unit circle, and they, like energies or eigenvalues, they repel each other. They do their best to stay away from each other. They will do this. They will be like ticks on the clock. So
there's no randomness there?
there's a very little randomness, very little. So in the limit, and we will explain, we get, so basically we will randomize the coefficients, and we will take decaying coefficients. In the case of fast decay, we will get a clock statistics for the eigenvalues. In the critical decay, we get this weak repulsion, which will be given by the circular beta ensemble from random matrix theory. And in the...
And you can get any beta, is that correct?
Any beta, yes, yes. Non-integer included. Any real beta between 0 and infinity. So, OK, so these are some plots. And let me now go back to the... So let me explain. For slowly decreasing random coefficients, we show that the eigenvalues are distributed according to a Poisson process. For rapidly decreasing coefficients, the eigenvalues have rigid spacing, clock distribution.
You define what these coefficients are.
No, I will define everything. I'm trying to advertise, and so that you follow me when I define the CMV matrices. And was because this transition is, it was quite nice to see this transition in the eigenvalue statistic. And for a certain critical rate, and I will explain what this critical rate is, we obtain the circular beta distribution for any beta. And so the transition from Poisson to clock, we see that the transition from Poisson to clock passes through a continuum of intermediate processes. And I will define everything. I will, I promise. OK.
That's a matter of taste.
Okay, so I will very soon. I will explain. So what is this transition? So we have this circular beta ensemble where beta is any real number between 0 and infinity. As we approach 0, we have the Poisson statistics. As we approach infinity, we have clock statistics. Okay, so I hope I convinced you that these CMV matrices are interesting. And let me just say that this transition resembles the transition in the bulk spectral properties of random Schrodinger operators. There's work by De Leon, Simon, Souillard, Kotaniu, Shiroya, Kiselev, last Simon. They studied random Schrodinger operators, and this is a random potential, random decaying potential, and they studied the spectral type of this random operator. And so if this random potential has L2 decay, then with probability 1, this random Schrodinger operator has purely AC spectrum.
Sorry, you mean that it's not uniform in space?
It's not the, so if you take the, let me show you. If you take the usual Anderson tight binding model.
We need the dimensions, sorry. One.
Dimension 1. Dimension 1, yes. So in dimension 1, the discrete Schrodinger operator in dimension 1, where you take the potential V1, V2, you don't take them to be identically distributed. You take the potential to be independent, V1, V2, V3 independent, with decaying distributions. So for example, something like this, a distribution which is uniform between -1 and 1, divided by n to a power. So uniform distribution between -1 and 1 divided by n to a power. As n tends to infinity, so the range for Vn will become smaller and smaller.
These are Fourier harmonics? What is Vn?
Vn are the, when you take the Anderson tight binding model. So you take, as a matrix,
That's right. No,
V1.
it's non-variant.
no,
It decays. You've got some
It
decay
decays.
in the potential. So the ANs are random, independent, IID. You divide by n to the power.
So this is one-dimensional chain.
Right.
Each hopping.
No, hopping's the same.
hopping is the same. All the,
Hopping's the same.
you have what?
Decays.
Potential decays.
Potential decays.
Along the chain.
Yeah, it is like
Like this, like
apply
this
some
power.
force.
Scattering Prof.
See this end of the signal.
Yeah,
So the ANs are IID.
But you divide them. So they shrink on the diagonal. They are independent but not identically distributed. And now this power here, the sigma, tells you how fast they decay. And depending on sigma is bigger than 1/2, that's fast decay. 1/2 is critical decay, smaller than 1/2 slow
So
decay.
this means that from one end of your chain, so you have a chain, at one end you have the strongest disorder,
Right.
and
Then the
disorder
disappears
decays.
and eventually should be metal down there.
Yeah, it should be.
Yes.
Well, I mean, extended states.
So, but this is in the bulk. I mean, this is the spectral type. So you have the transition. Fast decay is pure AC to pure point through purely singular continuous spectrum. And so what we do for this CMV matrix is we look at the finer structure of the spectrum. We look at the eigenvalue statistics.
And what is known, if at all, about eigenfunctions statistics?
There is work. So, for example, there is work by Kilip and
Say moments like moments sum of psi to some power.
no, they studied the eigenfunctions are exponentially localized. So they studied, for example, the distribution of the peaks of the eigenfunctions.
Exponential localized irrespective of time.
No, that's not.
No.
They're not exponential. It's some other decay.
But they always decay.
Yeah.
Oh.
Well, you said it's a pure point spectrum if sigma is less than 1/2.
Only in this case we have.
Depends on sigma.
Only in this.
Only in this case when we have slow decay.
Slow decay.
Okay.
It's not exponential.
Probably moments non-trivially scale with systems.
This has to do with this power sigma.
Exactly.
Everything's in this power sigma.
So sigma greater than 1/2, this will be the fast decay. So will be
you have
L2
AC.
decay. So we have purely AC. Sigma smaller than 1/2, we have slow decay. So pure point spectrum. And in the critical case, there are some regimes where the
But
purely
somehow,
single
if it decays too fastly, this means that the eigenfunction have no space to be localized somehow.
Exactly. There's not enough scattering.
There's not enough space for it. The disorder disappears faster than it gets localized.
Yes. But the critical, there's a critical point that's a half,
I see.
and then at a half,
I see.
all kinds of things
I
happen.
see. So the mechanism is this.
So and this was the inspiration, and this is what we had in mind before we started the eigenvalue statistics. Okay, so now, okay, I have to explain what this, excuse me?
In the fast decaying case, what is the distribution of eigenvalues in that case?
So the eigenvalue statistics
Yes.
is possible. That's work by
You
Mihai.
have fast decay and you have AC.
Oh no, slow decay. No, that's not no. That's not no. I will talk about this later. There is very recent work, less than a month ago, for the almost Matthew operator. So I will say something about the eigenvalue statistics in the end for this. But let me now tell you about this CMV matrices, how they are constructed, and how we observe this.
But their relatives is the ones you've just explained to us, right?
And I'll try to explain how they are connected to Jacobi matrices. So, and maybe I'll try to give you a hint, or like why we were able to get more results here, and why this problem was more tractable than the random Schrodinger operator. Okay, so the CMV matrices are matrices, unitary matrices, infinite unitary matrices, depending on parameters alpha 0, alpha 1, alpha 2, and so on. They are complex numbers of absolute value less than 1. And we should think about them as the unitary analog of the Jacobi matrices. So in the same way, when one constructs the Jacobi matrix, which is a self-adjoint matrix, a tridiagonal self-adjoint matrix, with coefficients alpha 1, alpha 2, alpha 3, b1, b2, b3. So the role of those coefficients, a1, a2, a3, b1, b2, b3, in the Jacobi matrices are played by these coefficients here, alpha 1, alpha 2, alpha 3. These are called Verblansky coefficients. So now this CMV matrix, this unitary matrix, is a 5-diagonal matrix as opposed to tridiagonal matrix in the self-adjoint case. So, and it's constructed in this way. And I have to tell you what this, so you see I have here these coefficients, alpha 0, alpha 1, alpha 2. So alpha 1 complex conjugate alpha 0, different expressions. And these rows here, rho k is square root of 1 minus absolute value of alpha k squared. So I construct this tridiagonal matrix. And now you can check that by multiplying columns that this is indeed unitary. And I will explain how we get this form. As I said, these numbers are called Verblansky coefficients from Samuel Verblansky. So we will want to study, let me go back a little bit. We want to study these unitary matrices and their spectral properties. And of course, this is an infinite unitary matrix. What we want is first to see how can we truncate this matrix. So first of all, for a self-adjoint matrix, there's no problem. If we have an infinite self-adjoint matrix, we truncate and we get an n by n self-adjoint block. With unitary matrices, there's always a problem. If we just cut the upper left corner, this could be not even normal. So we can do spectral theory with the, okay. So we have to be very careful. That's a big difficulty in the unitary case, how to truncate and how to take a finite CMV matrix.
You want to take a finite one and maintain unitarity.
Exactly, yes. So now, and basically it's like imposing a boundary condition. So what we impose here, you see, there's this rho k, which is square root of 1 minus absolute value of alpha k squared. If we force, for example, alpha 2 to have absolute value 1, then rho 2 will be 0. And you see here, rho 2 appears here, 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 and here. So if I impose the nth Verblansky coefficient to have absolute value 1, then what will happen, this infinite unitary matrix will decouple into a finite n by n unitary matrix and the rest. So we have this, we have to be careful how to decouple this matrix. Okay, so we will look at this upper left corner, this unitary matrix. And we will consider random Verblonsky coefficients and study the asymptotic statistical distribution of the eigenvalues of this finite matrix. Asymptotic meaning that we want to take a limit as n tends to infinity. So we get an n by n unitary matrix, randomize all these coefficients. Now, we have to remember that the last one must have absolute value 1, randomize these coefficients, and take a limit as n tends to infinity. So,
What does CMV stand for?
CMV, just 2 minutes. I will get there. So 3 Spanish mathematicians who I will explain. And it's their paper is from 2002. It's surprising how a very natural idea was, it turned out that it appeared in the literature in electrical engineering papers before, but it became popular among people working in approximation theory, orthogonal polynomials in 2000, 2004, and so on.
But there is no connection with any natural ensembles of symmetric matrices of self-adjoint matrices.
No. The construction is purely.
So if you take the logarithms of it, you don't see.
No, let me. Okay, I need to speed up a bit. So I will explain how this is constructed from orthogonal polynomials. Okay, so this is the random CMV matrix. Alpha n minus 1 with a random variable uniform distributed on the unit circle. So that's the last coefficient. And for the other coefficients, we have various ways of randomizing them. So, for example, we can take the other coefficients, all the other coefficients to be independent identically distributed on the disk. Or we can take them to be independent identically distributed uniform on the circle. And other things. So, for example, for the models that I showed you before, you can take them to be independent random variables, but alpha k uniformly distributed in a disk that shrinks in size, 1 over k plus 1 to sigma. So in here, as in the case mentioned before, we can identify slow decay, which is sigma is smaller than 1/2, which also contains the case of no decay when sigma is 0. Critical decay and fast decay.
Is it essential that alpha k's are complex?
Yes. So, but I will give you the background on CMV matrices and orthogonal polynomials on the unit circle. Then I will explain the main results in a rigorous way, main steps of the proofs, and open questions. So, background on CMV matrices and orthogonal polynomials on the unit circle. So there is a one-to-one and on-to. So I want to show you how to construct these unitary matrices starting from complex coefficients. So there is a one-to-one and on-to correspondence between measures, orthogonal polynomials on the unit circle, complex numbers, these Verblonsky coefficients, and the CMV matrices. So
what are the finds? Measures? You got to measure. What's fine?
orthogonal polynomials on the unit circle.
Oh, finds or orthogonal polynomials. Okay.
So 4 different types of objects. Okay. So how do we start? I want to explain how to start with measures and construct orthogonal polynomials. Let's consider 1z squared functions in this Hilbert space, L2 of the unit circle with respect to the measure mu. Take these functions, apply Gram-Schmidt, and we get a family of polynomials, monic orthogonal polynomials on the unit circle, phi 0, phi 1, phi 2. So phi n has degree n. And they are orthogonal in this Hilbert space. Now, so I have measures, polynomial, orthogonal polynomials. How do we get the corresponding coefficients? Well, it turns out that these polynomials satisfy, just like in the case of Jacobi orthogonal polynomials on the real line, they satisfy a nice recurrence relation. So phi k plus 1, the k plus first polynomial, is z times phi k minus a coefficient times phi k reversed. So I have to tell you what this is. So phi k reversed is obtained from phi k by taking all the coefficients, reversing the order, and taking complex conjugates. So so we start with any measure, and you get orthogonal polynomials with respect to that measure, and then you write and there is a recurrence relation satisfied by these polynomials, and then these coefficients appear here. These are the Jablonski coefficients. And so now I have to explain how, and this is one-to-one analogy.
If you wanted to express
Yes.
phi star in terms of all the phis, that would be a horrible expression.
Phi star in
It's
terms
still
of...
a linear combination of the orthogonal polynomials themselves.
Yes.
But probably
But the nice thing is that phi k plus 1 depends only on phi k and phi k star. So of course you can write this as a combination of 1, phi 1, phi 2, phi 0, phi 1, phi 2. But then it's nice that there's only one number here that gives phi k plus 1. So you know phi k, you construct phi k star, and with the help of only one number, you get the next polynomial. So this tells you that this recurrence relation tells you how to construct the next polynomial. If you have phi n and alpha n, you get phi n plus 1. Okay, so as we said, these polynomials are called the Jablonski coefficients associated to the measure mu.
But why it is important that the absolute value of alpha k is smaller than 1?
This is a theorem which says, in this recurrence relation, these numbers, one can show that these numbers are.
No, but if you take the modulus bigger than 1, what happens? So you also can
it's the
construct some.
definition.
But those are not. You can construct these polynomials, but they will not be orthogonal polynomials corresponding to a measure. So if you start with a measure, the coefficient obtained here is a complex number of absolute value less than 1. So now I have to tell you how to get from here and how to get that unitary 5-diagonal matrix, the CMV matrix. Okay, so if you remember, in the case of Jacobi matrices, you again have a recurrence relation. So you start with the polynomials 1, x squared, and so on. And you have a recurrence relation. So if you get the polynomials p0, p1, p2, p3, and so on, x times pn is a linear combination of pn plus 1, pn, and pn minus 1. Those coefficients, the three coefficients, you can take them from the recurrence relation and construct the Jacobi matrix, which is a tridiagonal matrix. Okay, so, and it's a band matrix in the self-adjoint case. Ideally, we want to get a band matrix also. So, so here's how one gets a band matrix. Okay, we consider one z inverse, z squared, z to minus 2, and so on. These form a basis for this Hilbert space. It's not hard to see that this is a basis. Okay, and we apply Gram-Schmidt for this basis. And instead of polynomials, we get a basis of polynomials, like in the, here you will get a basis of Laurent polynomials for this Hilbert space. It turns out that if we consider the matrix representation of this operator, f of z, multiplication by variable, in this Hilbert space, so the matrix representation of this operator with respect to this basis of Laurent polynomial, this is the 5-diagonal matrix. And
it's obvious that it's 5-diagonal because of the structure of how you set this thing up with this. Is that true or not? No.
It's clear that you can go. It's clear that you have at most two diagonals, two non-zero diagonals, and 0 below.
Yes.
But why we have exactly 2 above? That's a little.
That's a little bit more subtle.
Yes. So, so this is the matrix representation with respect to this basis is a is the CMV matrix. And now, with this, we have a complete picture and a one-to-one correspondence. Measures, CMV matrices, Jablonski coefficients, and it's a nice way of describing parametrizing measures on the unit circle. Okay, so, now a little bit of history. So Cantero, Moral, Velázquez wrote this matrix in 2002 in a paper. So they were Spanish mathematicians working in orthogonal polynomials. So they were basically interested in studying orthogonal polynomials on the unit circle, and they discovered that this way of writing a matrix and the matrix representation is this nice 5-diagonal matrix.
So what their motivation was what?
To understand orthogonal polynomials
Okay, so
on the
it was
unit
just
circle.
it was really, it didn't come from. I thought maybe you said something about electrical engineering or something.
Oh no, there was there was before. So there was matrices like this were but not these people.
Okay.
They are mathematicians.
Now you're saying though that all the matrix elements of this matrix come from the Jablonski coefficients,
Yes.
which were a different construction.
Yes.
Just
It's
usual.
it's very nice. Yes, that this CMV matrix, this 5-diagonal matrix, you use the Jablonski coefficients to construct the matrix representation of this operator, multiplication by variable in L2 of the. And the reason why this is appealing to mathematicians working in spectral theory is because it's a band matrix. So one hopes to decouple it and to, as I explained before, right? It's not too bad to decouple this. You just change one coefficient and then the matrix
So
decouples.
somehow this matrix has much less parameters than the usual, classical random matrix, because it has n squared minus n over 2
But for three-diagonal
matrix
matrices, you usually
elements and only
But,
n
yeah.
parameters.
Yeah.
for usual three-diagonal random
For Jacobi matrix.
Schrödinger, you have just n potential. That's it. The same number of degrees of freedom.
For Jacobi matrices or Schrödinger, you have
It's the same number.
Yes, yes.
A1, A1, A2, A2.
Yes.
Now here you would say, oh, but here I have 2n. And here it seems that I only have n. But I have 2n also because these are complex numbers. So this alpha. So it's indeed, I think, an analog. So, okay, now a nicer way of representing this matrix and thinking about this matrix is this LM decomposition. So L and M are tridiagonal matrices where, with each Jablonski coefficients, we can construct this 2x2 matrix, right? That's the basic 2x2 unitary matrix. And if we put them on diagonals like this, and here we put the even ones, and here we put the odd ones, starting with 1, the product of L and M is exactly C. So this is a friendlier representation of the CMV matrix. Okay, so now,
Would you go back to that for a second?
Yes.
So it's obvious that's unitary, right?
this yes, you multiply the.
Yeah. So obviously that's unitary. So product of unitary is unitary.
So each L and M are nice unitary.
Nice representation, but it's not immediate to see it from the first definition.
Oh, absolutely. No. I mean, from
It's
that,
not really.
no. And it's actually, it's not a great idea to show that matrix and say, oh, this is an interesting matrix, because
Do these two matrices represent some other operations on the Hilbert space that you can sort of, so Z somehow decomposes into two operators?
yes. So one is, well, the way in which this decomposition is by changing bases. So basically, if you choose different bases, and it's basically a change of bases in 2 steps. And if you carefully change the bases from 1Z, Z inverse, I think you switch the order, and then so you get from basis B1 to basis B2, and from basis B2 back, and you get this nice representation. So now, one thing I would like to say, what does it mean from the spectrum, from the point of view of the Gram-Schmidt process? We want to impose the alpha n to have absolute value 1. This means that the Gram-Schmidt process stops. So if you have...
You mean alpha n equals 1 for some fixed large n or not?
Yes. So
You're not
when
following.
if you start with a measure, on the circle,
That's the truncation procedure, right?
the truncation procedure, right? The truncation procedure corresponds to the case when the original measure has is trivial, has only finite, is supported on finitely many points. So, but what now going back to an earlier comment. So this recurrence relation can be used. We don't need all these alphas to have. We can write polynomials, right? Put any coefficients here, and we can construct the next polynomial. So now, of course, they are orthogonal polynomials only when these complex numbers alpha n are of absolute value less than 1. Now, if it happens that this that alpha 0, alpha 1, alpha 2, up to alpha n minus 2 have absolute value less than 1, and the last one has absolute value 1, this is not an orthogonal polynomial corresponding to a measure. But it's called a para-orthogonal polynomial. So because
Para or
para, para orthogonal. That's a definition used in approximation theory. So so basically we can also look at these polynomials where we take alpha 1, and these are not orthogonal polynomials, are para-orthogonal polynomials simply because I'm changing the last coefficient. And so the nice result, and this is probably the key to everything, many of the results that we get, is the fact that if we study this unitary matrix, this n by n unitary matrix, and we're interested in its spectral theory, the eigenvalues of this matrix are exactly the zeros of these para-orthogonal polynomials. And this result is the key and the connection between approximation theory, so the theory of orthogonal polynomials and zeros of orthogonal polynomials, huge literature in the field, and spectral theory. And this allows us, playing on this, right, allows us to derive. Results. Okay, so as we said, right, we will consider n by n finite CMV matrices with random coefficients. And so what happens if we take the first n minus 1 coefficients to be independent, identically distributed on the disk of radius r? The last one is uniform on the circle. Then we have Poisson distribution. And remember, this is the case of no decay. You can also put circles. So
the limit of n going to infinity.
As n tends to infinity. And I will make this in a little bit. I will make this very rigorous in a little bit. What I mean by this, what limit of a certain quantity gives a Poisson law. So disk, circle, Poisson. In the case when we have decay, depending on the decay, so if I take alpha k to be uniformly distributed in the disk of radius 1 over k to sigma, depending on sigma, we have, in the case of slow decay, we have Poisson, as we announced, circular beta ensemble when sigma equals 1/2, and clock when sigma is greater than 1/2.
Now you have to be, I guess, that statement 2 needs to be a little bit more precise, right?
Absolutely. I need to explain, because there's no beta here, right? So, of course. I need to say sigma equals 1/2 and a certain coefficient will give me the circle beta ensemble. So I'm trying to
But this clock is actually stronger correlated than the Wigner-Dyson, right?
Much stronger.
Oh, yes.
equidistant, like the
It's
ticks.
freezing of the, I mean, essentially it's like
Yeah, zero temperature. Yeah. So
Maybe, or is it more like just Laplacian? I mean, just take Laplacian and look at this, look at its spectrum.
yes, and then they are fixed in position. Now in this case, I want to show you, and I'll show an example of why we get the clock and the circle. But okay, so this is a picture that we have in mind. Now, rigorously, what does it mean that we study eigenvalue statistics? So we take a probability space, we put these coefficients in disks with uniform distribution, circle with uniform distribution. This is our probability space. Alpha is an element of the probability space. And we look at this random matrix, n by n random matrix, depending on alpha in this probability space. And we take a point, e to I theta, on the circle. And we look at eigenvalues located near that point. And we will look at eigenvalues in intervals of size 1 over n near this point, right? Because if I take an n by n matrix, so I'm looking at, so I fix an energy, e to I theta, and I'm looking at eigenvalues near this. And I want to ask, what's the probability when I fix an interval here? What's the probability of having 3 eigenvalues in this interval? And then I want to take the limit as n tends to infinity. But the problem is, as n tends to infinity, the size of the matrix grows, and also you'll have more and more eigenvalues. So I need to rescale the interval as n tends to infinity. So that's why I say here that we're looking at intervals of size 1 over n near e to I theta.
Can you do it for wider intervals or not?
For?
Wider intervals. 1 upon n is pretty narrow. Is that the best you can do?
The best, yeah.
Just to have a photo of 1.
Yeah.
Yes. I mean, per unit volume, I need to get
I
the.
understand.
So
I guess the typical scaling.
I want to scale by the size of the volume, by the size of the matrix. So how do we make this even more rigorous? So I take the eigenvalues of the CMV matrix, and I put Dirac delta measures there, and I construct a random measure. So for every eigenvalue, I put a Dirac delta measure. I get a random measure, which is a point process. And so when I apply this point process to an interval, this is a random variable, because this is a number of eigenvalues situated in interval I. And we study, so this is the result. This is formally the result. So if I fix a bunch of points, so intervals, A1, B1, A2, B2, A and B, and I say, what is the probability that in the first interval, A1, B1, e to I theta 0 plus, but rescaled by n. So I take the interval rescaled by n. What is the probability that I have k1 eigenvalues in this interval? K2 eigenvalues in the second rescaled interval. Km eigenvalues in the nth interval. And this satisfies the Poisson law.
Does it really mean theta 0 there?
Theta 0 is the fixed point.
That's the fixed one.
It's any position. It's completely homogeneous.
A fixed point, e to I theta 0 is a fixed point.
But you consider different intervals. This one and the next time again theta 0.
Yes.
Yes, it's a fixed point. Yes, I'm looking locally, microscopically near the eigenvalue e to I theta 0.
Not at different places.
No, I can't do different. That's open. I can take an interval here and an interval here.
It's false then, right?
Why?
No.
No, you expect it to be true, right?
You do expect it to be
Of
true.
course. I mean, if they're not correlated, I mean, what kind
I
of
don't
laws
know.
can
I'm
I don't
asking.
know.
It would be very nice to
No, but you expect it to be true, right? Or not?
From those numerics, it seems that
The
it's
picture
true.
looked like
yeah, the
very
It
picture
did
looks
look like it. It did look like it. I agree.
but
What is the
No, I'm not sure that you can.
so Poisson, it's basically locally Poisson. So I fix an energy, and I'm looking at intervals near that energy, near that point, which are scaled by n.
No,
Okay.
just
Locally Poisson.
you have to read because you look at different energy intervals. I don't know whether they're completely independent.
Yes, because of rotation invariance. Although I was very careful when I took the distributions for the alphas. I said disks or circles.
Right.
And actually, this is something that I can't get away with. I mean, I need to have.
So there is invariance.
I have rotation invariance.
Rotation.
If I don't have rotation invariance, I can't do this type of analysis. So, okay. So this is what I mean by Poisson, locally Poisson near every e to I theta 0. So, okay. So we have Poisson distribution when I have product of disks and product of circles. And just one word, this work was motivated by the results for Anderson models obtained by Stanislav Molchanov for 1D Schrodinger operators in 1980. and by Nariyuki Minami in the multidimensional Anderson tight binding model. So he also obtained these local Poisson statistics for the Anderson models. And in both cases, there was the same result, right? Near a fixed energy, we have local Poisson statistics.
In the Anderson model, the independence of eigenvalue which are far away is known, I guess, or is it
It's
not?
not far away.
No, these are near.
Yeah, I'm asking for the Anderson model. Do you know what happens if the two are not at distance?
No.
But you have to be in the localized phase to have this.
Right.
So what is the-
So in the Anderson model, the result of Minami is you look at energy E0, near which you know that the density of states exists and is positive. And the Poisson statistics.
No, but you can have a metal is fine. It does
No,
some
but
steps,
it's definitely close to the age, spectral age, probably.
Why? I mean, how do you
No,
know
he's
what
in
speculation
the
is?
localized
What-
space.
Yeah.
Minami's in localized space.
Yes, I think it's just by this.
It's only localized
Dynamics,
space.
the upper bound is in both conditions, I think, but the lower bound is in localized. So it's always at most Poisson. I mean, they cannot get close together, the eigenvalues. The Poisson statistic gives an upper bound, I think, for everywhere in the spectrum. But in the localization regime,
Okay.
you can also prove a lower bound.
Okay. So the one thing to mention here that Minami. So there's always you see these Poisson statistics when we got this result. The Poisson law here was basically the Lebesgue measure here. I take the Lebesgue measure of the interval A1, B1. You can have Poisson statistics with any measure. You can put here mu of the interval A1, B1. So Minami's result says that you get the local Poisson statistics near energies where you have positive density of states, and the probability measure, it's Poisson with probability measure, density of states times Lebesgue. So the density of states is, which makes sense.
So they also don't know independence at different places.
No. That's a very interesting problem and open, as far as I know. So if you take two energies and if you study distribution of eigenvalues here in this rescale interval, rescale instead, if you rescale near two different energies, that's an open problem.
You expect them to be independent, right? I mean,
Yeah.
I guess it's
Well,
not.
like that, but probably it's different.
We have
It's not so simple.
our methods just don't work.
Your formula, you cannot just take this A to be equal to N. In this, you cannot do it because then.
This A,
So A, you have this theta 0 plus A over N, right? And A1 over N plus
Yes,
A2 over N.
yes.
And you cannot take these A's to be of order N.
No.
So, okay, I need to speed up a little bit. I want to talk about the Poisson clock transition. So what is I want to explain the clock, right? So what is the very fast decay? So very fast decay is the case when all the alphas are 0, right? I mean, let's see what happens in this case. So if you take the recurrence relation, if all the alphas are 0, you basically you get polynomials 1, z squared, and so on.
So,
Yes.
Is this just a model case? We should
Model case, the simplest possible. The simplest possible. Let's see. I want to explain why we even get clock,
Okay.
right? So when we want to do fast decay, right? Let's say yeah. So what we get here, the orthogonal polynomial is what? Is z to n minus. Remember, the last coefficient is 1, has absolute value 1. So basically, you're looking at the zeros of this polynomial, right? And of course, these are roots of unity. This is a perfect clock. That's why we get clock in the fast decay case. Okay, now, so we want to consider CMV matrices with more general coefficients. And here I need to emphasize this. We need to take, in order for these methods to work, we need to take distributions for these coefficients that are rotation invariant. Simply because, basically, if I multiply a CMV matrix by a complex number of absolute value, that's also a CMV matrix. Now, if I want these two matrices to have, random matrices to have the same distribution, I need to have rotation invariance. And this is something, and this also explains why I can take any energy when study the distribution of eigenvalues there. Okay, so I can study, as explained, I can study complex numbers, so distribution of random numbers on the circle, or I can study just their arguments, which are real numbers. So theta 1 of alpha, theta 2 of alpha, theta n of alpha. Now, so I can look at these complex numbers or these real numbers. So either I'm looking at these complex numbers in rescaled intervals that rescale by n, or I'm looking at these real numbers multiplied by n, right? Would be, basically that's how I need to rescale somewhere, either at the level of intervals, at the level of points. So, so I can look at these point processes, rescale point processes on the line, and the point process is the sum of Dirac delta measures. And I need to take its limit, the limit of these point processes. So how can we take a limit of point processes? So if I have a sequence of point processes on the line, I would like to take the limit of this object. This can be done in two ways, which are almost equivalent. One is what I showed you, via number of points in interval events. So you have, you take, what is the probability that this point process has k1 points in A1, B1, k2 points in A2, B2, kp points in AP, BP, and take the limit of these numbers. Or we can take convergence, so we can consider these Laplace functionals, which are obtained in the following way. If the point process is this, we for any function f, maybe I should move this. For any function f, we apply f to every point, take the sum, and take e to minus that sum, so that in most cases, we get something that converges. So, and then we take, for any f, we take the limit of these expectations. So these are called the Laplace functionals, and we take the limit. So these are two ways of this one is fractionally stronger than 2. So we have 3 point processes which will be our candidates. One is the point process, the Poisson point process, which is with right. So I have probability of having k1 in eigenvalues A1, B1, kp in AP, BP is given by this product. The corresponding Laplace functional, which is a nice computation for Poisson, is this. So this is what we want to get in the limit. The clock or picket fence. I will write the Laplace functional. The Laplace functional is given by this. So if you want to have spacing h, the Laplace functional of the clock or picket fence process with spacing h is given by this. You see, it's as if you apply f to random translates in the interval 0h. So you have hk for any k plus x, and you integrate on 0h dx. So this is the Laplace functional of the clock point process. And I want to explain the circular beta ensemble with endpoints. Now this is something studied in random matrix theory. So let me tell you for endpoints, the circular beta ensemble with endpoints. So we have, imagine n random points on the unit circle, which give an ensemble which is like n identically charged particles on the unit circle interacting with this, by this logarithmic law, the two-dimensional Coulomb law. And this is a long gas. And so if you have f a symmetric function, and you apply the symmetric function f to these n particles on the unit circle, and you take the expectation, this is the integral of that function, that symmetric function, times the van der Monde determinant to power beta, and divided by this partition, normalizing constant. So, which has, it's computed, I checked Mehta's book, the derivation is there. So, so this is the circular beta ensemble for endpoints. Now, I'm saying that we get this as a limit as n tends to infinity. So I need, first of all, as an offshot of this work, if we get the following result. For any beta, if we do the following thing, if you take on the circle, if we take the arguments, and if we look at the arguments and we rescale them by n, so what do I mean? Take the points on the circle beta ensemble, n points, unwrap the circle, rescale them by n, and take the limit as n tends to infinity. This has a limit as a point process. And it's exactly the limit that we get for the eigenvalue statistics for the...
And what is beta determined by?
Yeah,
beta is a constant number. I'm sorry? Yes?
Yeah, we don't understand how the beta enters.
Related
Not
to
here.
alpha.
Particular case,
Not
how
here.
it
No, you haven't told us how the beta enters into the...
Absolutely. I'll show you the theorem, yes. But, and this is the limit of this thing is what we call the microscopic thermodynamic limit of the one-dimensional law gas, right? So we have the law gas is for n particles, but we want to take a limit. So what we do with it is we unfold it, rescale it, and take the limit as a point process in the sense of Laplace functions. Okay, so theorems. This is a paper to appear early next year. Suppose that all the random variables alpha k have rotation invariant distribution. So, in the case of slow decay, what is the slow decay? The expectation of alpha k squared, an absolute value, is bigger than 1 over, it's slower than 1 over k, basically. That's what it is. 1 over k to epsilon minus 1, epsilon is positive. And the technical condition. So I need this to be small. So that's fractional power. Then the eigenvalue point process converges to a Poisson point process with this intensity. So, example, 1 over k to sigma, where sigma is smaller than 1/2. Okay, so all we need for this is a rotation invariant distribution, construct the corresponding CMV matrix, and I require the expectation to be slower than this. And I must say this technical condition. Then we get Poisson. Critical decay. Here's where beta comes to play. The expectation of alpha k squared is like 1 over k times 2 over beta.
It's just the coefficient, really.
Is the coefficient that multiplies 1 over k. Plus an error. And again a technical condition. Then for the corresponding CMV matrices, the eigenvalue point process corresponding to circle beta
It's
ensemble.
probably the most non-trivial part.
Absolutely, absolutely. And
It's very non-trivial process to which it comes.
absolutely. What saved us was the fact that there's work by Kilip and Menciu in 2004 where they constructed an n by n CMV matrix which had exactly the circular beta ensemble with n particles. And we were able to see that basically that's a generic behavior. And we matched the constructed model.
But is there an analogous statement to this for the random Schrödinger than the Jacobi case or not? No.
No.
Volodya, Prof, I think I just recall some of your paper with on this power law and matrices.
Yeah, but here what is critical, I mean, we never had beta ensemble, anything like this, because...
But you had, I think, Wigner
No, but they were not tridiagonal. I think this is
no.
Exactly. So, and
But
the
just
question
I
was about
tried to see
tridiagonal.
analogy.
Yeah, I know.
I think there is some.
I think that here the critical distribution is built. I think it has repulsion at small distances like x to power beta, right?
And in your case,
No.
Yeah, so this is the case constant over square root of k, right? So this would be, this constant is 2 over square root of beta here. If you put it. So in the case of fast decay, when these expectations grow faster than 1 over k, then the eigenvalue point process corresponds to a clock process with spacing 2 pi. And that's the case of fast decay. So we see sigma is greater than 1/2. Now, okay, so there are I have 4 more minutes. I'll be happy to answer questions about how we prove this and other ideas. Let me just briefly show a few open questions and tell you what's recently discovered, very nice development in the case of Anderson models, so almost Matthew operators. And I want to show you also statistics, a numerical one now. Okay, so if, again, everywhere we assume that the coefficients in this matrix were rotation invariant. We can do anything in the case when they are not rotation invariant. That's a very, very critical assumption for our analysis. So understand anything about this would be interesting. Also, replace, right? So this is replace and study the spectral probability, even in the bulk, so the spectral type, when the probability measure is something like this for alpha 1 of alpha 3. So these are very interesting open questions. Okay, and like a dream result. Study the eigenvalue statistics for Anderson model. In particular, for example, like this critical behavior, which would be like for the multidimensional Anderson model in the conjectured metal insulator transition. I mean, that's no, I'm just.
It will be different type.
Of course, no, but like so. Like the flavor of this result.
In any type of simulations, to the best of my knowledge, it has never been seen that the repulsion of levels, 2-point correlation function at small distances, is other than simple beta, which is given by
1 to 4.
Beta equal 1, beta equal 2, beta equal 4. So there was no evidence that there could be some non-trivial beta at small distance. The overall distribution is tricky. So the tail is tricky, so everything
but the
is
short
tricky.
range is governed by the symmetry class of in other words, if I'm looking
Even
at
if-
orthogonal, I'll see beta equals 1. If I have unitary, I'll see beta equals 2, even in the critical regime.
Yes.
And it's just that the longer
And
distance...
field is not the case. as far as
No,
I
certainly not. Yeah. Good. Thanks.
Interesting.
So let me just, before I show you one numerical, numerical simulation. So less than a month ago, at the end of September, Avila last Simon proved the following result. If you take the almost Matthew operator, so which is this Schrodinger operator with not so much randomness, the almost Matthew operator, in the case of AC spectrum, so when lambda is smaller than 1, they proved the clock eigenvalue statistics. So you have, like, if you do the same thing, take an energy, rescale them properly, then we get the eigenvalue statistics for this. And of course, open questions. Lambda equals 1, it's hard, the critical case. Lambda greater than 1, that's still open. And the methods that worked in the Anderson model don't apply here because we don't have enough randomness. So, okay, and just one thing I want to show you. I did this simulation, just one picture to have in mind after this talk. So we have this transition. So we have, as beta goes from 0 to infinity, we have the circular beta ensemble everywhere. And at 0, we have Poisson. At infinity, we have clock. So we have this transition Poisson clock as we change beta. So what I did this numerical simulation. I looked at the eigenvalues of a CMV matrix. And I looked at the spacing between the eigenvalues in the arguments. And I did histograms with these spacings. So, for example, in the clock distribution, so when beta is large, we need to see that the spacing is almost the same. So basically, the histogram will have one tall histogram and nothing else, right? Because we have the spacing is constant. In the Poisson case, when we plot the spacing, we need to see the exponential. Because the spacing for a Poisson process is obeys the exponential law. So let me show you the plot. So this is what happens when I plot these histograms as beta goes from large values to small values, from clock to Poisson. And you see all these are from the case when I have circle of beta.
You're going through betas, right?
I'm going through betas. And then when beta is large, I have one tall histogram clock. When beta gets small, I get the...
Yeah, of course, because beta, in terms of the statistical mechanics, not just temperature, as you mentioned. It's for freezing.
Of course.
Yeah. Just they take position of minimal energy.
Yeah.
So that's, and I will stop here and I'll be happy to answer questions.
Okay, thank you very much. Well, I think you had a lot of questions during the talk, more than usual, I have to say. But maybe there are other comments or questions.
I think it's just that very nice that there is a real model where these all betas come very natural.
Yeah, and all in tridiagonal. I mean, or pentagonal, whatever you want to call it.
And all, as you mentioned, could be that also in Mathieu case, critical point you have just very.
Yeah, who knows? When lambda, like in the critical case, the almost Matthew, the transition between metal and insulator, the eigenvalue statistics.
But I still think it will be very interesting for your finite truncation and then for limiting process to study statistics of eigenvectors or what we call inverse participation ratios, the sum of components to various powers, how they scale with size of your truncation. I believe it should reflect your criticality and also non-trivially scale with your sigma. And I would just wonder what you will have at transition point when you have different betas, how it's, I think it's very...
So this different, I would like to ask you and other experts, you mentioned to me the band model for n by n matrices,
yes,
where you have a power fall off, which
yes,
is 1 over x,
yes,
which is critical for that.
Right.
And do you know what the eigenvalue statistics are as a function of the coefficient of the beta of 1 over x? Is it all analogous to what we hear here?
It's in some sense, no, it's different. Indeed, depending, so what is the model? Model, you have self-adjoint matrix, but variance decays away from diagonal as a power.
Yes.
And if this power crosses some critical value, I do not remember, it depends on your normalization, it's either 1/2 or 1.
Then if you take the variance should decay
as damage, as 1, yes. So if it's 1, then it's a transition point. For faster decay, you have Poisson statistics. It's not. I don't think that there are any proofs, but there is numerical evidence, also analytic evidence on the level of theoretical physics. So it's.
But fast decay would be the I think.
Be like Jacobi almost. If
slow decay. Slow decay would be.
But still, it's power law.
Power law.
Then, if it's critical, it's very much resembles. Now we believe that this is very good toy model in many respects, and also in very fine respects for just critical statistics at Anderson transition. And then with some small differences, but they are more or less understood.
You have multifractal structure.
Yes, and with multifractal structure.
Multifractal only at the critical.
I understand.
Yes, only the
so
critical.
So he may have multifractal structure of his wave function.
Yes,
He
but then
Yeah.
what Volodya mentioned, that it's for small spacings, it's still always these beta, standard beta.
Yep. Yes. Standard
And also
beta.
there is another important thing which is almost obvious. If you have fast decay, so which
Yes,
corresponds to localized,
yes,
this is a power law localization.
yes, but for spectral
it
statistics,
cannot be exponential because at one hop,
Of course. One hop, you're
it
jumping.
hops
you're
everywhere with the
But-
power.
Volodya, it's completely correct, but still for spectral properties. you
No,
have also-
of course, but I'm talking because you also asked
Yes.
about
But the
eigenvalue.
Eigenvectors.
So it is very,
Eigenvector.
very specific
Yes, of course.
eigenvalue distribution.
But there is
Eigenfactor.
but there is a multifractal character to it or not? Or
No,
it's not.
for larger than critical, no.
No, at critical.
It's not like
At criticality.
only
right?
at criticality.
At
Criticality,
criticality.
there is, yes. And
But-
there is also parameter, basically a coefficient, if you'd like. Okay, you can make it in various ways, but you can make a core where all entries are more or less equally distributed, not decaying, and then decaying.
Yeah,
And
sure.
using the size of this core as a control parameter,
Yeah.
then you will have the whole family of critical theories with varying multifractal exponents depending on this core. It's like the
I
whole
see, but
family.
as you're pointing out, as you guys both pointed out, you will not get a variable beta because the beta will be fixed by the symmetry
Yes,
class
yes.
and nothing more.
But
But you'll get
critical
different,
exponents
you'll
will
get
change.
different, away from short distances,
Yes.
you'll get different behavior.
For example, if you have this core very narrow,
Yeah.
in fact very pronounced, then it's very much close to local.
Yep. Well, let's thank Mihai again.